Hi, I'm Tim Eldred, and today we're going to be talking about scanning transmission electron microscopy, specifically the capabilities and data obtainable from this method. For scanning transmission electron microscopy, or STEM, an electron beam is focused to a probe. This probe is then scanned over a sample in different scanning positions. The beam then interacts with the sample and is scattered, and a detector below the sample collects these scattered electrons and allows us to form our image. One of the primary methods for low-angle scattering is Bragg scattering, which will be covered in detail in another video in this series. However, Bragg scattering is a constructive interference method that is dependent on the beam wavelength as well as the interplanar spacing. Bragg scattering takes place in electron microscopy in two major forms. We have selected area diffraction, where a more parallelized beam passes through the sample and creates diffraction spots, or converged beam electron diffraction, or CBED, where a focused beam generates disks rather than spots. CBED is more commonly done during STEM, whereas selected area diffraction is more commonly done during conventional TEM, although most scanning transmission electron microscopes are also capable of this method. For selected area diffraction, each Bragg diffraction spot represents one plane in the crystal structure. From this data, we can then calculate the lattice spacing along those planes. We can use that information to calculate strain and phase. From the relative intensities, we can capture orientation and diffuse scattering as well. From CBED, or converged beam electron diffraction, we can capture sample thickness, strain, phase, orientation, tilt, and even composition. In addition, we can also see Kikuchi bands. Now, these features originate from Bragg scattering and are more visible in thicker samples as compared to thin samples. They are fixed with regard to the reciprocal lattice of the crystal, and what they provide us with is a way to measure orientation, tilt, and also allow us to tilt the crystal to go from one zone axis to another zone axis to line up the atomic structure in a way that is suitable for our imaging. After the beam has passed through the sample, we can then begin image collection. One method is high-angle annular dark field imaging. This method uses an annular or ring-shaped detector, and at each point, the electrons striking that detector are simply counted and reported as an intensity. The collection angle is fixed, as the detector is a simple solid piece. However, by adjusting the camera length, or the spread of the beam, we can change that collection in order to capture different intensities. For high angle, we collect from 70 milliradians of scattering on out. This removes the influence of structure and low order scattering, and is dominated by Z contrast, or contrast dependent on the atomic number. The data that we receive is a simple array of intensities. HADF images are sensitive to both sample thickness as well as elemental composition. In the image on the left, we see bright bands where the indium is located and dimmer bands where it is only gallium nitride. On the right, we see an atomic resolution HADF image. The brighter circles represent aluminum columns, but there are darker gray circles in between that represent nitrogen columns, which are less visible due to their lower atomic number. With HADF, we are now down into sub-angstrom resolution and the ability to capture column precision with picometer precision. Atomic composition can be further probed with methods like EELS and EDAX. EELS, or electron energy loss spectroscopy, measures the electrons after they pass through the sample and measures the amount of energy lost by the electrons while they interact with the sample. Energy dispersive X-ray spectroscopy measures the X-rays emitted when electrons relax into a lower energy shell. The electron beam strikes an atom, an electron is lost, a higher order electron then collapses down into that energy shell, and a characteristic X-ray is emitted. From these, along with the scanning of the probe, we can begin to capture elemental mapping. On the left, we show an EDAX map. Going from the left, we have the HADF, followed by the indium and the gallium concentrations, where we can see that the indium corresponds to the brighter bands in the HADF, and the gallium is a higher concentration in the darker areas. From EDAX, we can get chemical composition, and we can even get quantitative EDAX and get the atomic percent. With EELs, we get an entire spectrum that shows the amount of energy lost by interaction with the electron beam and the atoms. From this, we can not only get chemical composition, but we can also look at the atomic valency or charge. The image above shows manganese and the characteristic spectrum of manganese 2+, 3+, and 3.5+. In an EEL spectrum, you can calculate the ratio of these three species present in your sample. In conclusion, scanning transmission electron microscopy provides truly local information. We can capture real or reciprocal space information on scales from the angstrom all the way to the micron. It can be used to qualitatively or quantitatively determine a number of parameters, including the lattice parameters of your crystal, the strain that the local region is under, composition, including atomic charge and valency, and phase. These capabilities are only increasing year by year as new data analysis techniques develop to take a look at these captured intensities or new detecting methods to capture more information. Thank you.